Everyone, today we are going to discuss the problem of the day, that is the minimum score of path between two cities. So we are given n cities numbered from 1 to n, and we have given road I, which indicates from city A to city B and the distance between two, and it is bidirectional. We can go to from any city to, from city A to B, and we can come back also. Then we have given a score of a path between two cities and defined as minimum distance of the road in its path. So we have given that uh, suppose this is A, B, and this is city C. So the score of the city A to C, that will be the minimum of this. So what will be the score of A to C? That will be 2. So minimum of the both, right? And it is also given that we can uh, use the same road multiple times. So suppose if we have a city D, and we and if it is 2 and it is 1, so to go from city A to B, right? So it is 1, A to B, that is 2, right? But if we can go from here this way, and we can go B through D also. So what will be minimum of all will be this one, right? So our best answer will be 1. So we can use visit the B twice, right, in this path. So we can do that also. So let's see the intuition, right? So this is the problem given in the lead code, and we'll dry run this. So our first intuition is we have given a graph, right? And second is we have given a weighted graph, and the weight are positives, right? So this indicates that we can use the Dijkstra, right? Simple. So let's see dry run. We will dry run, and we will see how we can use the Dijkstra here, right? So things is very simple, right? So we will take a distance vector, right? It will be n plus 1, right? N of n plus 1 size. And this indicates the cities and distance from city 1 to that city. So initially it will be int max, right? And we will start the Rasta from here. So we will use a priority to, right? So the first from 1 we can visit 4 and 2, right? So if we visit 2, then it will be 9 comma 2, that will be the minimum, and we will update that we can reach 9, right? And we can visit 7, right? Node 4 with weight 7, so it will push 7 and 4, and it will update that we can reach 7, right? And again it will now at the minimum is 4, and this will be pop, right? From node 4 we can go to node 2, right? Which is with minimum as that was 7, and this is 5, minimum will 5, so we can visit with node 2 with 5, right? So it will update that this with 5, right? And now uh, and and now it will be the minimum is and it will push with 5 comma 2, it will push 5 comma 2, right? So the minimum is 5, so uh, it will see can from 2 where we can go, we can go to 3, and we can go to 1, right? So we can go to 3 with the minimum of 5, and 6 will be 5 only, so we can reach node 3 with minimum as 5, so we can reach node 3 with minimum as 5, right? And we can reach node 1 with minimum as 5, right? So the minimum is again, so this was pop, right? And this was 5, 3, and this is 5, 1, right? So now this will at the top, this will be pop. So from node 1, we can go to node 4 and we can go to node 3. So with node 3, we can uh, go to node 2 with minimum as 5, right? The 5 minimum of 5 and 9 is 5. So node 2 is already 5, so it will not explode further, right? And and now we can go to 4 with minimum as 7, right? So it will mark it as 5 and it will push 5 comma 4, right? So the minimum is 5 comma 3, that will pop, right? From 3 you can go to 2. So minimum of 5 and 6 is 5. It's already for, for it will, so it will not explode further, right? Because our condition will be we can only go to further distance if it is greater than the minimum of the mm, distance from that node and the given weight. So distance and given weight. So if it is greater, then we can only visit. That's the simple Dijkstra condition that we are using, right? And again, at last, then 5 comma 4 will pop up, right? That is 4, right? So that is sorry, that is 5. So our answer will be 5. So that's a simple institution of the Dijkstra, right? So let's go and see the code for this, right? We'll go and see what we have discussed. There is very simple code this is for there. So let me show you the code, right? Code is very simple. So it is like we are doing the same. That is, we have making the adjacency matrix, right? And we are initializing our distance vector, and we have taken a min heap that will store the minimum distance, total minimum distance up to that node and the node, right? And we are taking out the total minimum distance and the node, and we are visiting, and we are taking the minimum distance, and if it is less than the already visited, then we push and we explode further, and we are returning the node, right? So this is the minimum, that is the Dijkstra. Now, now we can see. So there is a second approach also, right? Since we have to return the minimum possible value, right? And the score is also the minimum of all the values, right? So we note we there is very clear institution is that the minimum fraction minimum function is a decreasing graph, right? What is mean by this? This simply means that this simply means that if you add any number, right? Suppose you are given as node, we can we can say that if we are given like you are given 9, 7, right? And we are given 5, right? So what is the minimum of all 5, right? And now if you add any number, right? So it will either 5 or it will less than 5. the idea is very simple that instead of there can be two possibilities, right? One possibility is that from from this node we are visiting to the target node and the shortest path, right? Shortest path will contain the our minimum value. But there can be possibility like in this case, this is 7, right? This is not minimum. We can go through this path. This path is giving our minimum value that is 5. So we have also given that there is possibilities, right? So this is node 1, 2, and 4. There can be also nodes 3 that is not connected also. So so we the I what I want to tell you that so we not need to use Dijkstra uh because it's already it's already given that we need to find the minimum value, right? And the score is also minimum. So if we visit a path, right? If we visit a path and if we visit it twice, right? And that is not minimum. So I am telling that suppose y- you visit from this path, right? This is 9, 5, and 5, right? So answer will be not change. If you visit again and again, how many times you visit, right? Answer, if answer is 5, that will not change, right? So the answer will be from if 1 and 4 is in a graph, so the answer will be the minimum node of so answer will be the minimum of all the nodes, all the weightage with because since all the nodes are connected and we can visit all the nodes, right? All the nodes are connected and we can visit all the nodes. So the answer will be the minimum of all the nodes. So there because we can visit again and again. So institution is very simple, right? So so the answer is like it is minimum of all the weights, all the weights of the graph because whatever the minimum, right? So what is the minimum we can go this answer because from any node. So if this is the 4 comma 2. From 4 comma 2 we can go to 1, right? So when if it is connected, if it's in this component, suppose it is we can take one example like 1, 3, and 4. So 2, 3, and 1 is 2 and 5, right? So it is like if it is connected now, if it is connected 1 and 4, 4, suppose it have to be we are given that it is connected, right? There is one possible path that means the 1 and n will be connected. So we can see that what will the answer the minimum of 2 and 3, right? 2. So the nodes cannot be there can be two components, right? So these two nodes cannot be connected. So we have to just check that if it is if it is connected, then we can find out the minimum of all possibilities, right? So now there is two ways. The first way is we can do the simple BFS, right? We can do the simple BFS from this node, and we will visit all the nodes, right? All the weights, and we will keep updating our minimum variable, right? And we will find out the minimum of all the weights connected with a component in which one is present, right? So is very that's institution, and let's go and see the code of the BFS, right? So let's go and see the code of the BFS. So if we see the code of the BFS is very simple. This is our adjacency matrix, right? And we are simply taking Q and we are making a visited so that we cannot get we can detect a cycle also because and we are taking our matrix. So we are this is simple BFS. We are taking out our the front node and we are visiting and we are updating our answer. If that is not visited, so we are visiting that node, and this will give us the minimum distance between two cities, and that will be our answer, and we are returning our answer. And if we see the time complexity, that is has reduced very much. So if we see the time complexity, so for the Dijkstra time complexity is V plus E log V, right? Okay. So for Dijkstra and for the BFS, the time complexity is V plus E, right? So we have removed the extra, uh, we have removed the extra log E, right? So there is one other approach since there are multiple components, right? So we can use DSU also. So instead of there is one approach also that we can since there is too many components can be possible, right? So this is also possible for 1 to 5, right? Suppose if in this case, right? So if we making DFS, so BFS it will all visit 2 and 5 and we get our answer. Another is we can use DSU also, right? What DSU do? It groups the component and uh, and by rank. So and in that DSU we will find the parent of one, and then we will visit uh, those only we will take the all the weights minimum weights of that component only. So that's the pretty. If you not understand DSU, go and watch and understand DSU. You will get that also. So let's go and see the code of DSU, right? So for the DSU, we always is it a fair way to make a class DSU, and it has the parent vector and the rank, right? And we are here initializing initially all nodes are parent of the self, and all is containing one node, so rank will be one, and we are finding the parent of X. If the parent is self, so that is that node is the our leader node, right? And in Indian, we are finding the parent of the both, and if the parent is same, we can return easily. If the rank of px is less than, then we swap it because we not want to do extra uh, if else, right? And now we are updating the parent of py as px, and we are increasing the rank of px because we have add extra nodes. The rank will increase, and here we are creating object of that, and we are here making the components right from the visiting all the ways, and after making the components, we are taking out the parent of node 1. That is the component from where we have to find out the minimum distance among all the cities, right? And we are again visiting through all the edges, and we are finding if the parent of that component is equal to parent of the one. So if that component parent is same as parent of one, means that means the both nodes are in the same component, the same graph. So and if that condition, we are just finding out the minimum distance of both, and here we are deleting out that object, and we are returning our answer. So that's the very nice approach. And there can be uh, simple the simple thing was to notice here is very simple, that since we have to find out the minimum possible answer and the score is also minimum distance of all, so does not matter that how we go to that node, and the answer can be will be the always the minimum value among all the connected nodes, right? So that was the things to think, and that's all for today.